A further assumption we made of the classical linear regression model, and when we use ordinary least squares as an estimation technique, is that the explanatory variables are orthogonal to one another. In other words, they're completely uncorrelated or unrelated to one another. So this is not an explicit assumption. It's not one of the 5 assumptions that I listed on a previous slide. This is what we might call an implicit or hidden assumption that we also need to make. So just to recap, this is the assumption that the explanatory variables are uncorrelated between themselves. We can distinguish between 2 different degrees to which this might not actually be the case in practice. And if the explanatory variables are correlated with one another in some way, we call this multicollinearity. So we can distinguish between 2 degrees of, or 2 categories of multicollinearity. The first one is what we might call perfect multicollinearity, where there's a perfect relationship between 2 or more explanatory variables, and the other situation we might call near multicollinearity. That is where there's a non-negligible relationship between explanatory variables. That is, the correlation between 2 or more of the variables is too high to be ignored, but where the correlation isn't perfect. Looking first at perfect multicollinearity, that would be the situation where there was a perfect 100% correlation between 2 or more of the explanatory variables. So for example, suppose we tried to estimate a regression model of the form y equals beta 1 plus beta 2x2t plus beta 3x3t plus beta 4x4t plus ut, and let's suppose it's the case that x3t is exactly equal to 2x2t. What would happen if we tried to use ordinary least squares and tried to estimate the model in that case? Well, intuitively, we can see that the model wouldn't have enough information from the variables collectively to be able to distinguish between x3 and x2, because obviously both of them have identical information sets, because one is exactly equal to twice the other. So in that situation, we couldn't use ordinary least squares to estimate the values of both of those parameters together. To use some technical terminology, if we wanted to use the matrix expression, and if you remember, the matrix expression for ordinary least squares estimator beta hat was x transpose x inverse x transpose y. If we wanted to use this expression, you'll remember that I said in order for this inverse of x transpose x to exist, there have to be some conditions that are met. And specifically, the conditions are that the x transpose x matrix must be of full rank. In other words, all of the columns and the rows of that matrix must be linearly independent of one another. If, on the other hand, we've got one or more of the explanatory variables that's an exact function of one or more other explanatory variables, then there will be some rows or columns in this x transpose x matrix that are not statistically linearly independent of one another. Therefore, the x transpose x matrix will not be of full rank. It will be a singular matrix, and therefore the inverse of x transpose x will not exist. So the implication of that is obviously we cannot use the ordinary least squares estimator if there's perfect multicollinearity between 2 or more of the explanatory variables. The solution is obvious. What we'd simply have to do would be to either remove x3 or to remove x2 from the regression model, and then the problem would quickly disappear. So whilst the solution to this perfect multicollinearity problem is obvious, perfect multicollinearity is very unlikely to happen in practice. The only situation where we could get perfect multicollinearity in practice would be the situation where we'd inadvertently included the same variable in the regression model twice. Now, it might seem that would be a very silly thing to do and something which we'd never actually do in practice, but it's surprisingly not too difficult to do that. Suppose, for example, we were estimating a model for stock returns, and our explanatory variable set included short-term interest rates, long-term interest rates, and a term structure measure. That is the difference between long-term and short-term interest rates. If we tried to include all three of those variables in the regression model together, then we'd end up with a problem of perfect multicollinearity. Because obviously, if we took the long interest rate variable and subtracted the short interest rate variable, we'd have the term structure variable. Exactly. So we'd have a perfect relationship between the variables. And the solution would therefore be to only include two of those three variables in the model rather than all three of them. Near multicollinearity, on the other hand, is the situation where there's a non-negligible correlation between two or more of the explanatory variables. That is, the correlation is not 100%, it's not a perfect correlation, but it's too big to be ignored. Now, how big is too big to be ignored? Well, unfortunately, there's no scientific answer to that question. All we can do is examine the correlations and try to determine whether, given that correlations are on a -1 to +1 scale, we think the correlation might be too big to be negligible. What would be the problems if near multicollinearity were present in the regression model? Well, the answer is we'd have the following symptoms. First of all, the R-squared for the regression model would be high, but it might be the case that the individual coefficients would have high standard errors. So the implication would be, if the coefficient estimates had high standard errors, all of their t-ratios would be relatively small in absolute value. That is, the t-ratios would be relatively close to 0. So we'd have a kind of bizarre situation where if we look at the model as a whole using R-squared, we think that the model seems to fit the data relatively well. But on the other hand, if we look at the individual coefficient estimates, none of those are significant. And normally those two things wouldn't happen together. Normally, if we had no significant coefficients, we'd have a low R-squared. And if some or most of our coefficients were significant, then we'd have a high R-squared. So sometimes we get this odd situation where we've got a high R-squared for the model as a whole, but no significant coefficients in the model. And this is one classic symptom of multicollinearity. The second thing that happens if we've got near multicollinearity between the explanatory variables in a regression model is that the regression model becomes very sensitive to small changes in the specification. So if the explanatory variables in the regression model had been orthogonal, that is, they'd been completely unrelated to one another, adding another explanatory variable that's correlated with all the others into the regression model would not cause the parameter estimates on the existing variables to change at all. If, on the other hand, there were small but negligible correlations between the explanatory variables, adding in another explanatory variable with a small but negligible correlation with the existing explanatory variables will only lead to modest or small changes in the values of the existing parameter estimates when we add this extra variable. If, on the other hand, we've got multicollinearity between one or more of the variables that we've included in the model and one or more extra variables that we later add to the model, then including this extra variable or not including it could lead to very, very different values of the parameter estimates. So we say the regression becomes very sensitive to just adding or removing one variable from the regression model. The final problem of near multicollinearity is, in a sense, a corollary of the first point. That is, because the standard errors for collinear variables are relatively high, that will mean that confidence intervals for all of those variables, parameter estimates, will also be very, very high. The upshot of that is that whatever null hypothesis we're interested in testing will probably have difficulty rejecting them. So therefore we say that tests of significance in that context will probably lose power. In other words, we'll find it hard to reject null hypotheses, even when the value of the coefficient we're testing under the null hypothesis is very different from the estimated value. So therefore, significance tests could give the wrong conclusions. If we had estimated a regression model and we found that we had some of these symptoms or all of them, and we thought there was a collinear relationship between two or more of the explanatory variables, what could we do about it? Well, the answer is, unfortunately, there's not really any very precise statistical test for multicollinearity. All we can do is adopt a very kind of simple approach, and the approach that's most commonly used and it's always possible to do this in the standard computer packages like eViews or Microfit. The simplest approach is to compute pairwise correlations of all of the explanatory variables with all of the other explanatory variables. So if our explanatory variables in the regression model were x2, x3 and x4, we compute the correlations of each of those variables with each of those variables. If we computed all of these pairwise correlations and we put the correlation estimates into a table that looked like this, and we found that the correlation between x2 and x4 was 0.8, then we might say that a correlation of 0.8 was too large to be ignored. And if we had the symptoms of multicollinearity and we found this correlation of 0.8 or 0.9 or minus 0.8 or minus 0.9, for example, we might think that that would be where the problem lied. So computing pairwise correlations between the explanatory variables might give us a reasonable idea of where the multicollinearity that we observe is actually coming from. There is a problem with this, however, and that problem occurs if we have a form of multicollinearity that's related to 3 or more explanatory variables together. So in the context of perfect multicollinearity, suppose that we had x2 plus x3 exactly equals x4, or long-term interest rate minus short-term interest rate equals term structure variable, as I said before. If we had a problem like that, or similarly if we had near multicollinearity, so that the correlation of x2 plus x3 with x4 was, for example, 0.9, then we wouldn't be able to detect a form of multicollinearity like that by computing pairwise correlations of the original explanatory variables. In fact, if we had a more complex form of multicollinearity like this, it would be quite difficult indeed to actually detect it in practice. And the only way to do it would be to kind of go back to some financial theory and think about what are the possible relationships that could have existed between the explanatory variables, and then to try each of those one relationship at a time. Finally, it's important to note that multicollinearity isn't a high correlation between the dependent variable y and one or more of the independent variables x. That would be not multicollinearity. Indeed, that's exactly what we want to see. So multicollinearity relates to relationships between the explanatory variables themselves. If we have perfect multicollinearity, as I said, the only thing that we can do is to remove one of the collinear variables. If, on the other hand, we've got near multicollinearity, there are a number of approaches that we can adopt to fixing this. One approach that we could use is to use some other kind of estimation technique that's explicitly set up to deal with variables that are very correlated with one another. For example, ridge regression or principal components analysis. Econometricians usually don't like to resort to these and often say that they bring more problems than they solve. In particular, if we use principal components analysis, we end up using a set of artificial explanatory variables that are created from the original explanatory variables. And by doing that, we lose all of the intuitive interpretation of the original explanatory variables. So econometricians typically prefer to use a kind of more ad hoc approach to dealing with multicollinearity rather than using a different estimation technique. Some econometricians would say that if the model is okay in every other respect, then we can ignore the multicollinearity. So if the 5 explicit assumptions of the classical linear regression model that we made are all satisfied, and if we're happy that the parameter estimates in the regression model accord with our economic theory, that is, they have the right sizes and the right signs and so on, then we can just ignore the multicollinearity. In many cases, multicollinearity will only make a small difference to whether parameters are statistically significant or not. So if something was going to be very significant, even in the presence of multicollinearity, it will probably still be significant. It's only in the most severe cases of multicollinearity, and only for very marginal cases, will the presence of multicollinearity actually make a difference. So one possibility is simply to ignore multicollinearity altogether. It's important to know that the presence of multicollinearity doesn't affect the desirable properties of ordinary least squares as an estimation technique, that it is consistent, unbiased and efficient. So even in the presence of near multicollinearity, ordinary least squares will still be consistent, unbiased and efficient. All that will happen is that it will be difficult to obtain small standard errors. We'll just get large standard errors and wide confidence intervals. We don't have a problem with consistency, unbiasedness or efficiency. If we don't want to ignore the multicollinearity and we decide that we want to do something about it, there are several kind of ad hoc approaches that we can take. The first and most obvious of these would be to drop one of the collinear variables. So if, for example, we found the correlation between x2 and x3 was 0.8, then an obvious solution would be to either drop x2 or to drop x3, and then by definition the problem would disappear. From a theoretical point of view, however, we might have a problem with this, because our financial or economic theory that we wanted to test might suggest that the variables x2 and x3 should both be in the regression model together. And if that's the case, then we want to leave them in spite of the multicollinearity. An alternative approach, which allows us to include the impacts of both x2 and x3, but in a way which doesn't kind of incorporate multicollinearity into the model, would be to change x2 and x3 into some kind of ratio and include that into the model. So, for example, what we could do is to construct a new variable x2t minus x3t, or a new variable x2t divided by x3t. And obviously, even if there were multicollinearity between x2t and x3t, by computing the difference between them or by computing the ratio between the two of these, we've allowed for both x2 and x3 to influence the dependent variable, but we've done that in a way where we've only included one composite variable in both cases. But once again, from a theoretical point of view, we might not be very happy with that solution, for the simple reason that maybe our financial or economic theory says that yt depends on the value of x2t and the value of x3t. The theory doesn't say that the value of y depends on the ratio of x2 to x3 or the difference between x2 and x3. So we might not be very happy with that solution either. A final solution, which often seems to work in practice, is to go out and collect more data. Many econometricians would argue that multicollinearity is more of a problem with the data than with the model. So that being the case, what we can do is to go out and get a larger sample of data. We could do that in the context of time series regressions by taking a longer run of data. For example, we could take a sample of observations that goes further back in time. Similarly, if we were doing a time series regression, we could switch to a higher frequency of data. So if we've been using quarterly data, we could switch to monthly data. If we've been using monthly data, if it were available, we could switch to quarterly or daily data and so on. This would work by increasing the number of observations, leading to an increase in the kind of information content in our sample. So that even if the correlation between x2 and x3 was still 0.9, we'd have more observations on each of those series, which would enable ordinary least squares to better disentangle the relative impacts of x2 and x3 on y. Also, we know that the standard errors are inversely related to the number of observations by construction. Therefore, increasing the number of observations in our sample will lead to smaller standard errors anyway, and therefore the impact of increasing the number of observations will be to partially offset the adverse impact of multicollinearity on these standard errors. And so in some senses it will kind of cancel it out. So there are a number of possible solutions to the problem of multicollinearity that we can adopt. A further implicit assumption we made when we used regression models of the form that we have done so far is we assume that the appropriate functional form for the relationship between y and the explanatory variables was a linear one. That is, we assumed implicitly that in the context of a bivariate regression model, we could draw the relationship between y and the explanatory variables on a straight line. So suppose, for example, that we were interested in estimating a simple bivariate regression model of this form. We've implicitly assumed a linear functional form for the relationship between x2t and x3t. What does that mean? Well, that means we're implicitly assuming that we could represent this relationship on a straight line. On the other hand, unfortunately in finance, there will be many relationships between variables that are inherently nonlinear. So for example, it might be the case that if we increase x2, it leads to a straight line increase in y up to some certain point, and then if we increase the value of x2 more and more, then the impact on y gradually tapers off. Similarly, it could even be possible that if we continually increase x2, then the value of y will actually fall to a lower value than it had before. So it might be the case that the relationship between x2 and y looks like this. This being the case, clearly if we tried to estimate this type of relationship using a standard linear regression, then clearly we get a completely wrong fit. So ordinary least squares, if it were faced with a set of observations that did something like this, would obviously try to fit a straight line, and the straight line might do something like that. So clearly we'd be very badly misrepresenting the relationship between x2 and y. Unfortunately as well, there are going to be many relationships in finance that are nonlinear like this. So for example, if we were considering the impact of the firm's debt to equity ratio on the value of the firm, so if we plotted the debt to equity ratio against firm value here, it's often the case that for firms with no debt, for them to issue a small amount of debt, it increases firm value, because often debt is a cheap source of financing for firm expansion and to finance research and development. But there will come some point probably when the firm has issued sufficient debt that issuing more debt might lead to the possibility of financial distress or insolvency and eventually bankruptcy. Therefore, if the firm increases its debt to equity ratio further, it will cause the firm value to fall. So we have many situations in practice where we could have the relationship between the explained and explanatory variables being nonlinear. So an obvious question to ask is, what can we actually do from a testing point of view if we have that problem? Well, the answer is one approach that we can use, and this approach is programmed up in standard packages like eViews and Microfit, is to use what's known as Ramsay's reset test. Now, Ramsay's reset test is a residual-based test for nonlinearity. So if we come back to our representation that we could write yt as a function of the fitted value for yt from the model and the residual from the model. Obviously, if there's a nonlinear relationship between y and the explanatory variables, and that's not captured by the model, that nonlinear relationship will end up being present in the residuals. So we can take these residuals and test those for nonlinearity. So the dependent variable in the regression to compute the Ramsay reset test is the residual. The explanatory variables in the Ramsay reset test are higher order powers of the fitted values from the estimated regression model. So for example, y hat t squared, y hat t cubed, y hat t to the power 4, and so on, up to y hat t to the power p. Why do we use these higher order powers of the fitted values in the regression model? Well, the answer is these higher order powers of the fitted values in the regression model give us a very parsimonious or very compact way to get lots of possible nonlinear actions between the variables. So, for example, suppose that our original regression model, let's just put one more explanatory variable in there, it was beta 3x3t plus ut. Then the fitted value from this regression model, y hat t, will obviously be beta 1 hat plus beta 2 hat x2t plus beta 3 hat x3t. Now obviously if we square that fitted value from that regression model, then effectively we're squaring the whole fitted regression here. So y hat t squared will encompass the variables x2t squared, x3t squared, and the cross product term x2t, x3t. So, by using these higher order fitted value terms in the regression, we are in a sense, capturing all kinds of possible nonlinear actions between the explanatory variables here and the dependent variable y, which won't have been captured in the original regression model and so end up in the residuals. So by using these higher order powers of the fitted values, we can get lots and lots of possible nonlinear interactions very, very simply. Obviously, if we also include y hat t cubed, then we would be allowing for x2t cubed, x3t cubed, x2t squared multiplied by x3t, and so on and so on. In most of the standard packages, we only use the square of the fitted values as being the highest power in the regression. So usually we only use y hat t squared and then we stop there. But it's possible, of course, to use any higher order powers that we want to. Once again, if we compute the reset test, there are two approaches that we could use to calculating the appropriate value of the test statistic. The first approach would be to do an f-test approach. The unrestricted regression would be this one in the slide. The restricted regression would be the one where we didn't include any of the higher order powers of the fitted values, so we regressed u hat t just on a constant and took the residual sum of squares. Then we could compute the value of the f-test statistic in the usual way. Another approach would be to use the chi-squared version of the test. So we would run this auxiliary regression of u hat t squared on a constant and these higher order terms in the fitted values, and then we calculate r squared from that regression and multiply it by the number of observations t. That test statistic would follow a chi-squared distribution with p minus 1 degrees of freedom, where p is the highest order term of the fitted values in the auxiliary regression. Obviously, it's a chi-squared p minus 1 rather than a chi-squared p because we don't actually include y hat t in the auxiliary regression. We start with y hat t squared. So the null hypothesis for this test would be that all of the coefficients on the higher order fitted value terms were jointly zero. So the null hypothesis would be that in this auxiliary regression model, beta 2 equals 0 and beta 3 equals 0 and ... and beta p minus 1 equals 0. So that would be the null hypothesis for this regression model. The alternative would obviously be of the usual two-sided form, and we would reject the null hypothesis if the value of the test statistic, that is t times r squared, was greater than the chi-squared critical value. So the null hypothesis would not be rejected if the linear functional form which we assumed when we estimated the original regression model was appropriate. So under the null hypothesis, we could say that the linear functional form is appropriate. Obviously, if we reject that null hypothesis, that would suggest that the linear functional form that we used in our original regression model was not appropriate, and therefore we'd have to estimate some kind of nonlinear regression model. Sorry, I've just noticed there's a small error there. That should run up to beta p in the way that I've defined it here. Either that, or we could start at beta 1 and then run up to beta p minus 1. It wouldn't matter which we did. But either way, we should obviously have p minus 1 beta terms in that null hypothesis altogether. So we run the test, we get the value of the test statistic. If the test statistic exceeds the chi-squared critical value, we reject the null hypothesis that the linear functional form for the original regression model is appropriate. We then need to think, well, what might be an appropriate functional form for the regression model? Well, unfortunately, because of its very general nature, and because of the fact that we can incorporate many possible nonlinear relationships between the explanatory variables and y in the Ramsay reset test, the Ramsay reset test doesn't really give us very usefully any idea as to what a better specification might be. There are two approaches that we could use when we're faced with a rejection of the null hypothesis in the Ramsay reset test. The first one would be to go back to our original regression model and add in these higher order terms of the original explanatory variables into that model. So, for example, if this was our original regression model, then what we could do is add to it some higher order powers. For example, we could add beta 4 x2t squared plus beta 5 x3t squared plus beta 6 x2t x3t plus some disturbance term, let's call it vt. So we could adopt this kind of approach, and if the nonlinear relationship between the explanatory variables and y was of this form, then we'd expect statistically significant parameter estimates on one or more of those new variables that we've added. So that's one approach that we could use. And obviously, we could use squared terms, we could use cubic terms, or whatever was appropriate. And hopefully, our financial theory will suggest to us which of the variables should be included in a nonlinear sense and which should be included linearly. That is, which shouldn't include any squared or cubic terms and so on. Another approach, which is kind of fairly unscientific and an ad hoc approach, but which often works in practice, is to switch to a model in natural logarithms. So if our original regression model was a regression of the level of y on the level of x2 and the level of x3, so now let's get rid of these extra terms that I've put in here and go back to our original model. What we could do, instead of adding squared and cubic terms and so on in that regression model, we could switch to a regression in the logarithms. So instead of regressing y on x2 and x3, we'd regress the natural logarithm of y on the natural logarithm of x2 and the natural logarithm of x3. So we'd have log yt equals alpha 1 plus alpha 2 log x2t plus alpha 3 log x3t plus some disturbance term, again let's call it vt. So we could run a regression of this form in the logarithms. Now that seems to work such that if we got the residuals from this original model, we might fail the reset test. And if we collect the residuals from this regression model in a logarithmic form, we might find that the Ramsay reset test is satisfied. Why does taking logarithms often work in practice? Well, taking logarithms often works in practice because taking logs is a non-linear transformation of the original variables, and taking logs typically can transform a non-linear multiplicative relationship between a set of variables into a linear additive one. So for example, once again, if we come back to this exponential regression model, yt equals a multiplied by xt raised to the power beta multiplied by e to the ut, and we take logarithms, that then becomes a standard regression model. And more generally than that, often it's the case that if we start off with a nonlinear relationship between variables and we take logarithms, we'll end up with a linear relationship in the logarithms. Notice that in what we call a double logarithmic formulation, that is where both the dependent variable and the independent variables are expressed in a logarithmic form, we end up with quite a nice interpretation for the coefficients. In the original model here, the interpretation of the coefficient beta 3 would be that beta 3 represented the change in y that would be caused by a unit change in x3. In the context of this double logarithmic formulation, alpha 3 represents the impact on y that a 1% change in x3 will have. So beta 3 is the impact that a unit change, a change by a value of 1 in x3 will have on y. Alpha 3 can be interpreted as the impact that a 1% change in x3 will have on y. So we still have a nice interpretation of the coefficients here, and indeed some people would argue that we get a nicer interpretation of the coefficients in the double logarithmic formulation than we do if we just estimate a regression model in levels. So if we fail the Ramsay reset test, there are a number of approaches which we could adopt in practice and which will often work.